All right. Hi, everyone. I'm Alex. You may know me from hits such as Flatpak and my work in GNOME, but recently I've been doing this work on this thing called ComposeFS. And this talk is going to be partly about what it is and how it works, but also how it slots into the container ecosystem. So the tagline I use is a opportunistically sharing verified image file system. It's a mouthful, but like image file system, you can imagine it's about mounting a file system. That's an image. Like a container image could be, but it could also be a system image for a full system thing, or any kind of image you wish to share and then reuse. And sharing is about having multiple of these images, and they share resources in some way. So it's more efficient to have multiple of them than each individual. And verified is that we want to, in some way, guarantee that we're reading what we're expecting to read. So the easiest way to explain how it works is by an example. Suppose we have this image. I mean, it's not much of an image, but it's basically files, right? And a structure, and metadata, and all that. And you run the mk ComposeFS command, and you give it the directory that you want to create from. You give it an example.tfs, that's a file name, and then you pass in a digest store, which is a directory name. And when you run this, you get this. You get the image file, and you get the objects directory that has a bunch of weird-looking things in it. Those things are just files. And if you go back to the original thing, we had a foo.txt and a bar.txt. And those weird-looking objects just have the content of those files in them. And the names are like checksums. And then you can, from this again, you can mount it. You're specifying the objects directory and the example file, and then you get back the same results. It doesn't sound all that exciting because you could as well just use a loopback mount for whatever kind of file system you wanted. The interesting thing is this particular objects directory. As I said, it has the backing data for these files. And if we were to change one of them to not be what it was supposed to be, and then mount again, you will see the new changed data. So basically, this directory contains all the backing files of the entire file system. So the interesting thing happens if you have multiple of these images that share the same base directory. Because these names are actually checksums, so any two files that happen to have the same content will have the same checksum, will use the same file. So that's what's called content addressing. It's common in Git and whatnot. And that's where you would get what I call opportunistic sharing, as opposed to explicit sharing, like Docker layering, for example. You have to be very careful about managing your dependencies, such that you used exactly the right base image and whatnot, and then you get sharing. But here you get wherever, for whatever reason, if you happen to have two identical files, they will be shared. And they're not only shared on disk. Because of the way ComposeFS works, when you mount this thing, if you mount two things, they use the same file, and something maps it or whatever, or just in the cache, they will be only stored once in the cache. And you can easily see how you could use this to update to a new version of an image and not have to download all the data. Like you can just download the image, list all the objects and see which one you don't have and download those. So it's like an automatic way to delta downloads, basically. And then to get into these verifying part, we have to look at something called FSVerity. FSVerity is a feature of the Linux kernel. It's been around for some time now. It's actually both a feature of the VFS itself and the individual file system. So it has to be implemented in each file system, and most of them are. Or actually, XFS is not yet supporting it, but there's work on that. But basically, you enable this on a file, and that makes the file immutable in the sense that the VFS will not allow you to do any operation on this that changes its content. You will get basically permission denied when you try to write to it or whatever. But also, if you modify the file directly on the block device or whatever, Cosmic Ray hits your drive and it flips a bit somewhere, when you read it back, there's a checksum That's like a recursive Merkle tree checksum across the entire thing. So whenever you read a block from a file that has been modified, you will get an error, an I/O error, basically. So that's pretty cool, but unfortunately, it has some weaknesses. Yes, you cannot change the file, but you can change the metadata. You can rename the file. You can, make it set UID or whatever. You can create a new file. You can delete it and replace it with a new one with the same name. It basically doesn't validate what we want, which is the image. The thing we want to validate is the entire image, the file names, the structures, the metadata, everything. So that's where we go back to ComposeFS. And if you actually look at the measure of the FS measure of this file, which is the digest, basically, like the checksum thing, it actually has the digest for name. Basically, we're using FS already on all these objects. And not only that, we also record the expected digest inside the image itself. So whenever the file system opens a backing file, it can verify that it's actually the right thing. And then, once you've opened it, each individual read from the file will be verified by the kernel. So if you mount it with Verity on, like you might not want this, you might want to use the sharing without the Verity if, for example, your file system doesn't support Verity. But if you do have it, like just enable it, and then when you read the file that we changed before, now we get some kind of error because it doesn't have the Verity digest we expected it to. So that helps a bit, but what we wanted was to protect the entire file system, right? And you could potentially write into this image file and change the name of a file by modifying the file. And to avoid that, we enable FS-Verity on the entire image itself, and then we pass the digest that we got. I mean, ideally, this digest you're not supposed to just read it from the file when you mount it, but at build time, you record the digest, and then via some kind of secure mechanism, a channel, secure boot, signatures, what have you, for some reason you trust this digest, and if you pass it to the mount command, if the mount command succeeds, then every successful I/O operation on this thing will be guaranteed to return the same data that was built. Basically, this is a root of trust. If you have a reason to trust it, you can guarantee the thing. There are some technical details about it. This talk is more about explaining the high-level parts. Initially, it was a completely new kernel file system. Actually, I did a presentation on the kernel dev room last year at FOSDEM about this. But during the upstreaming process, it was changed, so now it's using some existing technologies, OverlayFS in particular, and EroFS, that were already in the kernel, but they have instead been extended a bit, so they support this use case too. And OverlayFS is normally a way to layer things, but it actually has already a way for a file in an upper level to have a different name in the lower level. Normally you use that for renaming a file across layers, but we use it instead to redirect to the baster. And then we introduce this thing called data-only lower base directors or layers, and so we basically hide the lowest level and we just redirect to the files in there. And then we have an EroFS, which is an ISO file or a SquashFS. It's just a read-only file system that we use to record the entire directory structure of the loader and the OverlayFS, including like the file names and whatnot, and the OverlayFS X-adders that do the redirects to the lower directories. And then we use bind mount or loopback mount this thing and set up an OverlayFS combined thing to use it. We had to add a couple of things. The data-only lower directories to hide the lower directory. The FS-Verity validation, we had to add a new X-adder to OverlayFS to validate the redirects. And then there's some nested stuff where you have overlays in OverlayFS. That's kind of weird, but we had to add that too. But it's all in now. And we have a final version release that has a stable format that you can use, and we're supposed to work forever. We also have integration with OS3. I will not spend too much time on this, but O3 is our, like Red Hat's image-based entire system, like atomic immutable upgrading system, used by things like Fedora Silverblue. And the current version of O3 has experimental support for just creating these ComposeFS images. So we create them at build time and sign them, and then if you validate it during boot, like it validates the signature in the initramfs, and if it's valid, you can mount the ComposeFS image, and everything is just guaranteed to be whatever is right. And if you're using something like Secure Boot to make sure you boot the right kernel and you write initramfs, then you basically have an entire tamper-proof boot signed by your BIOS key, basically. But this talk is about containers. And ComposeFS has two major targets. It has the O3 use case and OCI images. And the actual work on Podman and the backends is done not by me, but by Giuseppe, who is one of the Podman and C-Run developers. It's based on his work on CSTD Chunked, which I'm not going to go into too much details here, but it's basically a new compression format for OCI images that allows adding an index to the file, and the index has the checksum of the files, so we can avoid downloading them if you already have them. But also the fact that we have these digests is a perfect way to introduce the objects directory kind of thing that ComposeFS uses. So if you look at container storage, which is the Go library for storing local images that Podman uses, the latest version has basic ComposeFS support. And we just have to wait until they vendor in the latest version into Podman, and then it should just work out of the box. And if you have this, we'll get some of the advantages of ComposeFS, like higher density. If you have any images in your cluster happen to share files, those files will be stored only once on disk, well, per whatever node you're using, and once in memory. And we can also use the validation to make sure we don't accidentally get modifications, but also in the future, this is something that needs a bit more work. We could have a list of signatures or a list of keys and like limit the amount of, or limit the types of image you run to only those that have a signed ComposeFS digest by these public keys. So how do you use this? There are some options in the storage.conf. You have to enable all of these currently. Actually, the convert images is not strictly necessary. That's for converting images that aren't in this new CSTD chunked format. So it works with any. If you pull any image, it will convert it to that format, and then you use ComposeFS for mounting it. So it will work for anything, basically. But if you want maximum performance and not have to do the conversion, it's good to use CSTD chunked in your image repositories. But that's something you want anyway in the future, at least, because you get to download less as well. If you ever looked inside the container storage, this is how it looks, a traditional one. Actually, I deleted some stuff, but the important thing, there's this per backend directory called overlay, because we're using the overlay backend. And every directory in there is a layer. And every layer has a diff directory that has all the files that are introduced in that layer. And then you use overlayFS to combine all of these, plus at the end it adds your empty directory that is the writable directory for your container. But instead, if you look at a ComposeFS using backend storage, it looks different. It has the same overall layout, but the diff directory contains basically the base dir, and then there's this extra data, the blob. So what happens is that when you set up the container, we mount all these ComposeFS directories, each producing a layer, and then we merge them in overlayFS, plus your writable storage. So it looks slightly different, but it's basically the same. And to demonstrate how this will affect resource usage, I created 20, so this is a synthetic example, but I think it proves the point. I created 20 copies of Fedora image, and I changed one file in each and squashed them so they're like single layer images that basically have all the same files in them. And then I run sleep in each of them. And sleep is a very small thing, but it will map glibc, and it will do like some basic stuff that any app would do. And then I run them all in parallel. And we could look at how this looks in the storage. Every file here is, or every directory, every layer is the Fedora base image, so it's 180 megs. Some up for 20 up to 2.5 gig. But if you look at the ComposeFS version, it's just 200 megs because only the things that are different use more space. And this might look weird that just one of them is larger, but actually what happens is that each individual layer has all the files that they refer to, but they're hard linked across directories. So there's like a tracking of which files are locally available, and instead of you making a copy of them, they're all like hard linked of each other. So that's pretty cool. I mean, I can imagine. It depends, of course, on your workload, but it's not implausible that different images share files, because most images are based on RPMs or debs, whatever. And if you have the same deb of a glibc package, then it will have the same file, even if you're using a completely different build of your image. So this is pretty cool. We're working on trying to like finalize this, make it work by default in Podman. I think it's going to miss the 4.9 release, so it's probably going to be in the next release. Also, the Podman people themselves are trying to work on making CSV chunk be more of a default thing, or more, at least more widely used, because it has advantages not only for ComposeFS, but also for just faster pulling of images. And then we need to look into signing images. I mean, there are ways to sign manifests already. And you can imagine if you add ComposeFS digest into the manifest and you sign the manifest, if you can validate that the manifest is signed, then you can trust the digest, and you can mount the thing and know you have the right thing. But there are outstanding questions like, yeah, but what kind of keys are you using? Where do you store them? How do you know which one you trust? You know, there has to be some kind of rule set to specify what you're allowed to, which keys are golden or whatever, or are we using the kernel keyring or the secure boot keys? It's like, there are outstanding questions, but the technical side is not really that complex. If you can validate using some kind of mechanism that the digest or that the manifest is okay, then we can just mount this thing and be able to trust it. And I guess
when it turns green, hi, thank you for your talk. I am one of the people who worked on PuzzleFS, so I was very curious to hear about this. One of the things that the design choice in PuzzleFS is different than ComposeFS is that the files are split along file boundaries instead of along sharing boundaries. It makes it easier to get cool graphs with USS, but harder to then share if you change small portions of a file. I'm curious if you have any, like, is that part of your future work? Have you thought about that problem at all?
I mean, I've thought about it, and I'm not going to do any work on that because it would require so much work on the kernel side that just like fundamentally change how pages are tracked and stuff. That's not going to happen.
Yeah.
So I mean, it's a choice you have to make if you want to focus on disk space use or in memory use.
Yeah.
I think this is sort of like a Goldilocks zone, but
yes,
it depends on your use case.
Yeah. Also, PuzzleFS was written in Rust, so it was impractical for other reasons.
Thanks for your talk. My question is about ComposeFS.
I didn't get the question.
I believe CSTD chant image format is...
Yeah, it doesn't really like... CSTD shunt is a way to extend the header of a layer tarball with information about what goes in it. And it's not strictly needed for ComposeFS. Like you can untar the tarball and compute the checksum of every file if you want to. But if it's there, you can avoid that, and it's just better performance. So it's not necessary.
Another question about the compression format. So the VSTP, I think, especially all the tools, I believe don't support the VSTP compression format. So, but GFrame is widely supported among tools, and create like index image format like the VSTP channel. But you use like a GZIP, for example, star GZIP or star GZIP.
Yeah, well, GZIP is the standard, right?
So, do you have any plans to support this GZIP-based index image format?
Yeah, there's this E-star GC thing that you could use for that. Like, I haven't spent any time trying to make that work. I mean, it will work. It just introduces a conversion layer, a computation of these things. But I mean, I think it could be done. I think it could be done, and if you have that kind of format, but you would still have to create an index for your GZIP files as well. And then, like, I don't know if E-star GC is better supported than CSTD shunt. It's unfortunate, like, the Podman people did the CSTD thing a long time ago, but it took a long time until Docker merged it. But in the latest version, like a year or so, they merged the pull request to add it. So it is actually supported by Docker now. So the hope is that eventually it will get wider acceptance. But it isn't perfect right now.
Hello.
Hey.
Maybe what's happened when the first container is shut down because maybe I understand this. All the others, the first share to run fine with the others, maybe also something.
So why would you run 20 sleep commands? Is that a question? Or?
Yes.
Yeah, I mean, obviously you wouldn't. You would run on your node 100 different containers, but any containers that happens to ship the Fedora 232-2 glibc RPM would have the same binary for glibc, and then that would be hashed to the same file, so everything that maps glibc would use the same file. I mean, this demo is just a demo to expose the sharing. It would be less extreme in the real case, but it would still happen.
Thank you. The question is, it might be a wrong use case, but this object storage directory, is there a way to clean it up after leaving a ComposeFS file?
It's not currently, but we have some issues around about adding tooling around that, like an FSCKA for it and a garbage collect for it and things like that. That's thing. All the code is there to read back from an image file and extract the list of objects in it. So it should be. Currently, it's possible by doing some scripting to do it, but we would like to add some tooling that automates that.
We have 5 more minutes, so would I ask a question? Okay.
Just wanted to know, is this something that you switch on existing tasks?
Yeah, I mean, it works fine. It's in Fedora now, and you can install it. Whoa. No, I mean, it requires, for all of the features, it requires the latest kernel. But if you have 6.5 or later, then it just works on any system. It's just a user space tool. Doesn't need any special anything.
Are there any changes required for just VLAN for this to be supported? Does it work? Are there any changes on the registry layer for Docker?
No.
Or does it just work?
It just works.
Okay, thanks a lot.
All right.